Hello everyone, welcome to our discussion of section 2.6 where we will be talking about constant of variation. Now constant of variation is typically seen in all fields of business, economics, management, and science. So it's everywhere. Formulas that we have typically have a constant of variation in them. So we need to know what they are. Now, there are two kinds of constants of variation as far as we're concerned in this class. One of them is called the direct variation, and it has a formula like this: y equals k times x, with k being the constant of variation. The only reason I use k on this worksheet as to refer to constant of variation is because most books refer to constant of variation as k. So most authors use that letter to refer to that. And then the second kind of constant of variation we have, it's called the inverse variation, and the formula for that is this. And of course you can see k divided by x there. So what makes the difference between these two formulas? How do we have two different formulas for each for these two types of variation? So make sure we understand that before we see some examples of this. So to begin with, k, or constant of variation, is really a ratio of y over x. You can think of it as that. Or I would prefer actually to think of it as k being equal to the ratio of the dependent variable divided by the independent variable, right? So these are two, you can think of it as y over x, or you can think of it as that, dependent variable divided by the independent variable. Now, for the direct variation, that is, all you have to do is rearrange the terms in this formula, right? K has denominator 1, and if you cross multiply, that means y times 1 and k times x, this is exactly the formula you get. So you get y times 1 times, or equal to k times x, and then of course you get that equation which I've highlighted in green. So that's where it's coming from. But that formula is coming from this relationship that I'm highlighting in yellow. It's coming from that k being equal to y over x. It's just a rearrangement of that. That's direct variation. Now, with inverse variation, with this one, once again, we begin with the principle that k is equal to y over x, right? Just like before. It's the ratio of the dependent variable divided by the independent variable. But because the variation is inverse, we're going to replace x with 1 over x because the relationship is in inverse. So therefore, instead of that, we write k equals 1 over x. Okay, that's inverse variation. So now let's manipulate this expression or equation algebraically. What do we get? Well, this is a compound fraction, meaning y divided by 1 is in the numerator, and then 1 over x in the denominator, right? So to simplify this compound fraction, we can write, let's multiply the terms that are farthest away from each other. We get x times y, and over divided by the terms that are nearest each other, which would be 1 times 1 or 1. Now, rearrange this formula and solve for y. So we get y equals k over x. Now this result is exactly what we have here, right? So this is just to show how this formula was derived. Everything you need to know about how it was derived is on the screen right now. Okay, so that's how we have the formula for inverse variation, and earlier we talked about the formula for direct variation. So now, what is the meaning, the conceptual meaning, or the difference between direct variation and inverse variation? Okay, so conceptually, when you have direct variation, what this means is that if you have two variables x and y, they either rise together or they fall together. So as one goes up, the other one goes up, and as one goes down, the other one goes down. A good example of direct variation is, let's say we're looking at a hot dog stand, right? The number of hot dogs sold is directly proportional to amount of ketchup used or sold by the hot dog stand, right? So if the salesman sells less hot dog on a given day, then the amount of ketchup is also going to go down. Less ketchup will be used during that day. If the number of hot dogs sold goes up, then the amount of ketchup used or sold will also go up. So that's an example of direct variation. Variables either rise together or fall together. Now, what's an example of inverse variation? There are a lot of good examples of this as well. But this inverse variation simply means that if you have two variables that are somehow correlated, then if they're inversely related, then as one goes up, the other one is going to go down. By the same token, as one goes down, the other one is going to go up. So the relationship is in inverse direction. They do not change in the same direction together. The direction of change is opposite to each other. So what are examples of this? Examples of this could be, okay, we have a job, let's say a job, we're trying to finish a job, right? If you hire 10 employees, let's say 10 workers to do this work, let's say it's going to take 3 hours to finish the job, right? What happens if the number of workers that you hire for this job drops? What if you have 5 workers that are working on this job now, right? Not 10, but 5. Then the number of hours it takes to finish this job, it's going to increase. Maybe it's going to go to 8 hours now. So do you see how this works? As one variable goes up, the other one comes down, or as one variable goes down, the other one goes up. You can see clearly that the relationship is inverse between the number of workers hired on this job and the number of hours necessary to finish the job. Another, I'm sure you've heard of this a lot, another famous example for inverse variation is the relationship between price and demand, right? If there is, let's say if there's a hot commodity such as this iPad that I'm working on, right? They are very, very popular. So for an iPad, if the price is, let's say just for the sake of argument, if it's $800, then the demand, let's say, could be $10,000. But if you reduce the price to $500, right, of course the demand is gonna go much higher, maybe $20,000, maybe $30,000. But you know and I know that if the price of iPads drop, the demand will skyrocket, right? So that's another. Demand and price always have an inverse relationship with each other. Okay, so now that we understand what is the role of this constant of variation, either directly or inversely, let's go through some examples. In this one, it says that in each case below, and I'm reading from here, In each case below, find a variation constant and an equation of variation for the given situation. The given situation, first of all, it says that y varies directly as x. Okay, so right away you can use this formula for this situation. If y and x are varying directly, we can make use of that formula. So let me write it down as that. Y equals k times x. Now, before I go further, let me remind you, as I've done before, it would be best if you pause the video at this time and answer this question on your own, and then come back to the video and compare your solution with this one. As you probably have heard me say in class, 90% of learning this material is your solution, and only 10% is my solution. So please don't skip the 90% part. Okay, so I'm assuming you've done that, and now you're back. Now we're going to use this formula and this information given to find the value of k. So we have 54 equals k times 12. Now solving for k, solving is always isolating the variable, right? So to isolate k, we need to get rid of that 12. How do we do that? We divide both sides by 12. On the right side, 12s cancel each other out. And on the left, we get 54 divided by 12, which is 4.5. So k is 4.5. So that we did the first task, we've already accomplished it. We found the variation constant. It's 4.5. Then it says, in the equation of variation. Well, all we have to do is plug this k value into this equation, and we have our equation of variation. So y equals 4.5 times x. And there we have it. Okay, that's the equation of variation. All right. So I hope this agrees with what you did on your own. Next one. The example, once again, the situation is that y varies directly as x. So that means we can right away write y equals kx, right? And now we know where that formula has come from. And we know what that means. It means that if x goes up, y goes up. If x goes down, y goes down. All right. So we're going to use this pair of information to solve for k first. All right, so, and I'm hoping that you've already finished your work and you're back to compare your solution with this. That would be great if you've already done that. So 0.1 equals k times x, or k times 0.2. And we're solving for k, so we need to get rid of that 0.2. So let's divide both sides by 0.2. And we have k equals 0.1 divided by I've already done this, so it is 0.5. We found the constant of variation. Now all we have to do is plug it into that formula. And what do we get? We will get y equals 0.5x, right? That's our equation of variation. Okay. So next one, please make sure that you have already answered this, and hoping that you're just back here to compare this with your solution. So y varies directly as x, so that means we can write that. And let's use this particular example to solve for k. So when y equals 1, x is equal to 1 over 4. In other words, we have 1 equals k over 4, and then we have k equals 4, right? We found the constant of variation. Now let's plug that into our equation to find y. So we have y equals 4x. And that's our equation of variation. Okay. So now after all this, let's have a look at a real world situation where we can make use of constant of variation. So here it says the amount of sales tax paid on a product is directly proportional to the purchase price. We know that to be true, right? The higher the purchase price, the higher the sales tax. Okay, it says in Iowa, the sales tax on a Nook glow light that sells for $119 is $7.14. What is the sales tax on an ebook that sells for $21? And of course, the assumption is that the ebook is being sold. We're looking to solve this in the state of Iowa. Okay, so the first thing we need to do is looking at how much the product, the glow light, this product, what cost, and how much the customer paid for as sales tax. We need to find out what is the sales tax on products sold like this in the state of Iowa. Okay, so let's do that. As you know, with all word problems, we have to introduce our own variables, right? Since we're talking about sales tax, I'm going to introduce T to represent dollars of sales tax. And of course, the purchase price is involved, so I'm going to use P to represent dollar amount of the purchase price. Like that. So we know how the relationship works between these two, right? The sales tax, and let's say K represents the tax amount or the tax percentage, however you want to calculate this. So then the sales tax would be, or the tax amount, maybe I should revise this. Let me revise this to tax amount. And so T would be equal to K, or the tax amount, times P, right? This would be the formula for calculating that. So for this particular example of the glow light, that we have the sales tax was calculated as $7.14 equals K times the price, which is $119, right? So let's calculate K. It would be $7.14 divided by 119. And so calculating that, I got 0.06. And usually, as you know, sales tax is represented as a percentage. So we can say either that or multiply this by 100, we get 6%. Either that or this, right? So now that we know the sales tax, and it says, what is the sales tax on an ebook? Now that we know the tax rate in the state of Iowa, then it says, what is the sales tax? And I'm reading from here. What is the sales tax on an ebook that sells for $21? Right? So we come back here, and we know that the price, this price is now $21. K is 6% or 0.06. So the tax on that merchandise, which is the ebook, would be K or 0.06. Make sure you use the K in decimal form, not in percentage form. So 0.06 times 21, and we get tax equaling $1.26. So this would be the tax on the ebook. Okay, so that's just one word problem for for variables that are directly proportional to each other. Okay, now with the inverse proportionality, variables that are inversely directed, then we already discussed that this is our formula. We talked about how we derive it, right? We've done that. So now let's apply it to a few problems. Right here, right from the get-go, we are told that y varies inversely as x. So go ahead, every time you see that, then you can use that formula. which is also on the formula sheet you can use during the exams. So you write y equals k over x. Now this pair of values that we have, we can use it to just figure out k. So we have 3 equals k over 12. And of course, the result of this is if you cross multiply, because 3 has denominator 1 here, if you cross multiply, you get k equals 36, right? That's the constant of inverse variation. And then it says also find the equation of variation. So all we have to do is plug this k value in this formula that we started with. And doing that, we have y equals 36 divided by x. Okay, so those answer the 2 questions for part A. And as I said before, maybe it's better that you answer these on your own and then compare your solution with these. So I hope you're pausing the video and you're not just copying my answers here. So that's the nice thing about videos. You can always pause and rewind and so on and so forth. So this one again is right from the get-go. It says y varies inversely as x. So right away you can use the same formula we have here. Y equals k over x. And then use this pair of information to solve for k. So we have 12 equals k over 5. Once again, you can cross multiply. You get k times 1, which is k. And then 12 times 5, which gives us 60. So constant of inverse variation is 60. And then and they're also asking for the equation of inverse variation. So all we have to do is plug this in here. And then we have y equals 60 over x. So that's the 2 things that they've asked us to find. And the next one, very similar situation, right? So we have y, we are told that varies inversely as x. So we can set up the formula as y equals k over x. And then use that and the pair of information we have to solve for k, right? Just using that pair. And we have y equals k over, so instead of y, we have 0.1 and x is 0.5. So just cross multiply once again. We get k times 1 is k, and then 0.1 times 0.5 gives us 0.05. So that's one thing that they've asked us to find. And then the other thing is the equation. So let us plug this back into this equation. And so we have y equals 0.05 over x. And so this will be our equation of variation in this case. So these are the 2 things that they asked us to find. Okay, and then we have one word problem that also for this situation of variables that are inversely are connected through a constant of inverse variation. So let us answer that. It says the weight of an object, and this is a really good example, and you'll see why, because it has an interesting twist to it. It says the weight of an object varies inversely, right there. The weight of an object varies inversely as the square of the distance d from the center of the Earth. From the center of the Earth, right? So, because this time, even though we're told, and let me write the formula first, it is y for inverse of variation, we have this formula, right? But because it says the weight, and now let me replace y, which is the dependent variable, right? In this case, weight depends on the distance d from the center of the earth, right? Based on what I've highlighted in green. Weight depends on distance from the center of the earth. So let me replace y with w like that, and I will replace x with d. Right? So our variables make sense. And so instead of x, I have d. Now the twist that I was mentioning earlier is this. It just doesn't say weight varies inversely as the distance. It says weight varies inversely as the square of the distance. That means we need to square this distance, but you can't just square this independent variable and not do the same thing to k. These two are connected. If you're squaring this element, then that element should be squared too. That's why we have the second power for the whole thing. For k over d, not just for d. Okay, just keep that in mind. So knowing that, it says, and I keep reading from here, it says at sea level, apparently the distance from the center of the earth is 3,978 miles. An astronaut weighs 220 pounds. Find his weight when he's 200 miles above the surface of the earth. Okay, so we need to find k, right? Otherwise we can't find w or his weight when he's 200 miles above the surface of the earth. So they gave us a bunch of good information we can use to find k in this case. So the weight in this case is 220 pounds. So we're going to substitute for, so we have w at 220 pounds. And the distance we already know. If he's at sea level, his distance to the center of the earth is 3,978 miles. So let's plug these two values into this equation and solve for k. So we have 220 equals k divided by 3,978, all of that squared. Now, to solve for k, we need to take the, let me bring that here. Then we have 220 equals k squared, right? Distribute the power into k and that. We can distribute the power because we have division inside the parenthesis, right? Inside the parentheses. So k squared over 3,978 miles squared. And then let me just, since I'm running out of space here, let me shorten this and say k squared is equal to this very large number. Make sure you do this on your own calculator to double check these numbers that I have. And if you find any discrepancies, please let me know. And we have that as k squared, right? So what is k then? K would be the square root. So we have to take the square root of both sides. And because we're talking about a constant of variation, we're going to take the positive value. As you know, when you take the square root, you end up with both plus or minus. So in this case, we just accept the positive. And so we have 59,003.27 as the constant of variation. So this is that. So in this formula, we figured out what k is. Now they're saying, what is the astronaut's weight and let me maybe highlight this in blue. What is the astronaut's weight when he's 200 miles above the surface of the earth? What we've done, we know that at the surface of the earth, he weighs 220 pounds. But what if he's 200 miles above the surface of the earth? Have you thought about, think about what in this formula, what would that affect, right? Because now we're looking for this piece. We don't know how much he weighs at 200 miles above the surface of the Earth, so we're going to look for that. And then, so it will affect the distance, won't it, right? You agree? So I hope you agree with that. So instead of 3,978, let me, since I'm a little bit short of a space here, I'm going to erase this and rewrite this. We're looking for the weight of this astronaut 200 miles above the surface of the Earth. You can see in here that we've already found what K is, right? K is 59,003.27, and we know in the formula we have to square that. Okay? Divided by the distance. Now the distance is the distance from the surface of the Earth to the center of the Earth, which is 3,978, but the astronaut is now 200 miles above this. So that plus 200 miles, and then we have that also squared, right? The distance is squared, the K is squared. Okay, so I hope you don't mind if I erase all of this, but you can always rewind the video and look at what was there. So now the weight of the astronaut 200 miles above the surface of the Earth is as follows. So if we, in the numerator, we have this large number, 85,871, right? And divided by this, add the 200 with 3,978 and square that quantity, and hopefully you get the same value I have here, right? Like that, and calculate that ratio, and you should agree that this weight is almost around 199.4 pounds. As we expected, right? So we expect that we weigh less in the outer space than we are closer to the Earth or on the surface of the Earth. And for sure, this agrees with that. So the astronaut weighs 220 pounds on the surface, standing at sea level on Earth, but he weighs 199.4 pounds, 200 miles above the surface of the Earth. Okay, I hope this worksheet or this video was helpful, and I look forward to answer any additional questions you might have, either during my office hours or in class. Have a good night.